Hi everybody, my name's Chris Collison. We're continuing to look at quantum mechanics, and we're working at the moment on the rigid rotor. And at this point, it also makes sense to think about why we're spending so much time with the rigid rotor. Well, we're moving towards the hydrogen atom. We know that the hydrogen atom will be is going to be very well described using spherical coordinates. We're at a place right now where we're actually going to complete this section and come to a conclusion about these so-called spherical harmonics. And the spherical harmonics describe the solution to the Schrödinger equation when the radius is constant. So we're going to start to think about what this all means as we move towards the hydrogen atom. So also just remembering from the last lecture, we considered the case and sort of more jumping right into this now. Here's our Legendre's equation. And we developed the Legendre's equation from the differential equation for the theta term from our separation of variables for the Schrödinger equation. So we had a theta expression. We wrote that down in terms of Legendre's equation, which I said was a well-known equation in classical physics. I put forward the solutions for m is equal to 0 in here. These were called the Legendre polynomials. And in this next section, what we're going to do is talk about the case now where m is not equal to 0. And in this particular case is called so we're going to do some, this particular case is called the Associated Legendre Functions. So that's defined. Actually, these associated Legendre functions are defined in terms of the Legendre polynomials that we just introduced. So let me provide a general expression for this equation. So I'm going to just say here, these are the associated Legendre functions. And let's write down this equation. So we will write it as P subscript J. So this is a subscript, and as a superscript, so this is not an exponent, so we're going to say this is a subscript, and this is a superscript, not an exponent. So this is a function of x, and this is the associated Legendre function. It is 1 minus x squared raised to, this is now an exponent, the magnitude of m over 2, and d raised to the power of 2 by dx. Sorry, raised to the power of m, raised to the power m at the bottom, multiplied by the p sub j in here. This is our Legendre polynomial. Okay, so it's defined in terms of the Legendre polynomial. Okay, that's what this statement says for us. So now I've pulled the Legendre polynomials from a prior slide, and they sit over here on the box on the left-hand side. So first of all, before we kind of jump into what, well, we can write these out, right? Eventually we can write out the associated Legendre functions, right? Because we have the formula. But before we do that, before we take a look at these particular solutions to that Legendre's equation, let me just state that only the magnitude of m is relevant Why? Well, because this all starts with a differential equation that depended on this m squared term. So right back when we did our separation of variables, we put the constant for the separation of the two terms, we set that up to be an m squared term. So therefore only the magnitude of m is relevant because, let's say, because this all starts with a differential equation depending only on m squared. So it depends only on m squared. So another thing when we think about m, right? So often people say to me, well, you know, we've got, knowing that we're going to the hydrogen atom, we have all these quantum numbers that we'll get for the hydrogen atom, and the quantum numbers depend on each other. So we're going towards that hydrogen atom, but right now we're thinking about these rigid rotor, these spherical harmonics. And so there's a situation where really m, we've stated how m cannot be larger than j, right? So m is less than or equal to j. So where does that come from? And so I'm going to say in here, you know, let's put a question mark in here. I'm also going to say, remember that the leading term in the Legendre polynomial, so is that x to the j term. And so the next thing I'm going to say is, well, what would happen, you know, what would happen if m were greater than j? So what we'll do is, let's suppose m equals 3 and j equals 2. So what we're now going to do is let's actually put together an associated Legendre function. So we're going to say, okay, j is equal to 2, so m is equal to 3. So our symbol for that associated Legendre polynomial, remembering that the 3 in here is a subscript and not a power term. Okay, this would be equal to, so let's go to our expression up here. So we've got a 1 minus x squared term. Remember, m is 3, so this is to the 3 over 2 in here. Now we've got our derivative, so d3 or d cubed by dx cubed. And inside the bracket here, we've got our Legendre polynomial, and remembering j is equal to 2, so this is the particular case over here. So in this, so we'll actually put let's just put the half in here and then separate that out. So we've got 3x squared minus 1. Now we see where we've got a problem, because the third derivative of an x squared term is going to end up being equal to 0, and therefore and so the case where m is larger than j does not give us a finite value. It gives us a value of 0. So the result of all that is that m is less than or equal to j. And so we've just demonstrated, you know, if we want a solution, we've got to have m being less than or equal to j. So what have I done now in this slide? With this particular example, I've just shown how we might build a particular associated Legendre function. Okay, we did it. This is a perfectly fine associated Legendre function. It's just, it turns out that this particular case isn't going to be a solution for our Schrodinger equation, and so we you know, doesn't exist. We don't care about it. At this point, I'm also going to say, you know, everything in our Legendre's equation is in the x term, and we've got to remember that x, of course, was equal to cosine theta. So the next thing we're going to do is actually say, we need to return home. We need to think about our theta function being in terms of theta and not x. So let's, after we've introduced these associated Legendre functions and we've recognized that these are solutions to Legendre's equation, let's now take this back to the original problem that we started with. And with that, let's just make a note of this. Okay, so remember, we've got to remember theta and not x is of physical interest. So what I'm now going to do is write down these associated Legendre functions. Okay, so the first one is P0. By the way, I've also added in here the Legendre polynomials that we've already discussed. So because we recognize, of course, from that standard description, which I'll also write on the side in here, this is the equation for our standard or our associated Legendre functions. So as I say, the first one is P0, right? And so again, what do we have in here? This is our J term. What do we have in here? Our superscript is our M term. So it turns out that that is simply equal to 1. Let's change color and we'll start to work on when J is equal to 1 and M is equal to 0. So we've seen this already, and that's equal to simply X. And now the important thing here is, of course, we are converting back to theta. All right, so this ends up being X is equal to cosine theta. So we keep going with our associated Legendre functions. So now J is equal to 1 and M is equal to 1. So again, if we use our equation over here, we've got the 1 minus X squared. M being equal to 1 gives us the square root, the half in here. And when J is equal to 1, we simply get the first derivative of X, which is simply 1 in here, right? So now we can start to understand that there's a 1. I won't write down the 1, it's implied. So this ends up being 1 minus cosine squared theta, which is sine squared theta, raised to the half, which is sine theta. So that's a fairly straightforward function. All right, it's a wave function already, P2. So now we're going to advance up to J is equal to 2. And again, we've got our, we recognize that now since M is equal to 0, this first term goes to 1. So we end up having 1 for that first time multiplied by P2 of X. And that ends up simply being equal to, so we can use the equation from the top right hand corner, 1/2 3x squared minus 1, and that's equal to, again, x squared is going to be cosine squared theta. So in this particular case, we end up with 1/2 multiplied by 3 cosine squared theta minus 1. So converting into theta again here. When J is equal to 2 and M is equal to 1, we cycle through. So now, of course, we go back to this 1 minus x squared term with a 1/2 expression in here. We've got the, of course, we've got the d by dx of the 1/2 3x squared minus 1 term in here. So now we start to get a little bit more complicated, but this ends up basically being 3x 1 minus x squared to the half. And because effectively we've got inside the brackets in here, we take the first derivative of the 3x squared, we get 6x, but multiply it by 1/2, we get the 3x on the outside. So this is the derivative piece. And what does this end up being? Again, using our trigonometric identities, I won't put them all in here. We get 3 cosine theta sine theta. Okay, so we're running out a little bit of room in here. These are getting a little more complicated. P2 2. So m can be equal to 2 when j is equal to 2. And that's now going to be, I'm just going to write down the results from now on. It's going to be 3 times 1 minus x squared. And that ends up being 3 sine squared theta. This is next up is we cycle through all the m values up to j equals equal to 2. So the next one is we go back to j equals 3 and we start with m equals 0. That will turn out to be simply our P3 term. We'll take the derivative of that. I'm sorry, we won't take the derivative of that. We'll just end up with the answer being 1 times 1/2 5x cubed minus 3x. Okay, and that will end up being, when we turn that into cosine theta, will end up being 1/2. I'm going to start writing this in a different color. Ends up being 1/2 5 cosine cubed theta minus 3 cosine theta. And the last one I'll do actually. So P3 1, m is equal to 1, j is equal to 3. Again, let's just kind of jump forward here. 5x squared minus 1, and that's the piece in the derivative with that 3. Right, so again, we're using this expression in here. So this is the derivative term, and then we've got the 1 minus x squared to the 1/2 because m is equal to 1, and this turns out to be 3/2 5 cosine squared theta minus 1 times sine theta. And we can go on, right? So etc. We can keep plugging these in. What else can we write in here? Let's draw up, remember the Kronecker delta. So let's summarize here. We'll say also this last expression was the expression that we would obtain with the Legendre polynomials. And what we've done here is just replace the x with the cosine theta expression in here and here. And we've reverted back to that, we recall that dx is equal to minus sine theta d theta. So what have we done in here? Well, you might say, where's the minus sign in here? We've got the sine theta d theta in here. Where's the minus sign? What we've actually done in here is we've changed the limits. So by changing the limits from originally it was 0 and pi down in here, but again, what we've done is we've accounted for that minus sign by putting the pi and the 0 in here. Of course, right? Cosine 0 is equal to 1 and cosine of pi is equal to minus 1. So you can kind of see the change that's taken place. If I didn't bring that up, you would not know what was going on probably. So we now have an expression. Here's our Kronecker delta in here. Let's just remind ourselves. Here's the Kronecker delta in here. And let's just remember that what we've done here is we've gone from dx equals minus sine theta. We've gone from dx to the sine theta d theta. The minus is in there as well. Let's go to the next slide. We're also going to remember the differential volume element. So again, what was that? What am I talking about? Well, you remember when we were thinking about a change to spherical coordinates, we had this region of volume of space in here, and these values were r d theta, and we had some thickness of the shell, if you will, that was dr, and then the other dimension in here was r sine theta d phi. Okay, so when we put all that together, we had a d tau, so that's our volume element, and that was equal to r squared sine theta dr d theta d phi. And so what we've got, right, so we made that substitution in the previous slide, right? So we had a sine theta d theta term. If we go back to the previous slide, here's our sine theta d theta term in here, and it turns out that that sine theta d theta term is really the theta part of d tau in spherical coordinates. So so these two pieces combine to provide the let's say the theta portion of d tau in spherical coordinates. So just trying to tie up some loose ends in here. So let's actually jump back to the associated Legendre functions. So we'll do the associated in the same vein now. So these associated Legendre functions, they need to satisfy the following expression. Again, just thinking about, again, orthogonality and normalization. So we'll plug this in as shown. Remember, now we've got our m term in here. And that is equal to, there's no complex numbers at this point either. So again, here we're going to rotate, so we're going to go from pi to 0. We're going to expect, therefore, the sine theta d theta term at the end, where we're incorporating that minus sign into the changed limits. So again, the goal here is just to change from the x term back to the cosine theta term. And it turns out that this ends up being equal to 2 over the 2j plus 1. So that comes from, we talked about that in the previous slide, that comes from the Legendre polynomials piece. But so now we've got this additional term in here that will be j plus magnitude of m factorial over j minus m factorial. Let's put and that's the Kronecker delta in here that again says that this is equally valid. Essentially for we're shorthanding it here and saying, well, yeah, this is representing orthonormality, so it takes care of our orthogonal case when j is not equal to j prime. It takes case of our normalized piece where j is equal to j prime. So we have a new normalization constant here. So this constant, we say, satisfies the normalization. So it also, if we think about it, when m is equal to 0, right, we're just going to, this term is going to cancel, right? So when m is equal to 0, we're just going to have j factorial on the top and j factorial on the bottom. So that will turn into 1. So that will return for us the normalization constant that we got for the Legendre polynomial. So kind of everything ties together at the moment. Another thing just to remember, by the way, just to remind ourselves here that 0 factorial is equal to 1, by the way. Okay, so our normalization constant is therefore, let's write this down as njm in here, and let's say that's equal to 2j plus 1 over 2, and then j minus m factorial, and this is over now j plus m factorial, and that is all to the square root in here, right? So what we've done is effectively, well, yeah, there's two functions in here multiplied by each other, so that, you know, if this expression on the right hand side in here satisfies the normalization condition, then we've got to take the square root of it, and then we've got to, you know, bring it back over the other side to put this constant in front of our associated Legendre function in order for when we square those terms and integrate from pi to 0 in order to give us that one term. So have a think about that normalization constant. You know, obviously we've got now the 2 in the denominator, whereas before we had it in the numerator, and we just flipped these around, right, because we brought them over to the other side of the, so that we end up having a 1 on the right hand side. You know what I'm talking about. Okay, so in the next slide, I'm going to sort of finally tie everything together. And so we're going to take this normalized theta part, we're going to build it in with the normalized phi part, and we're going to regroup everything together to get the y, that y eigenfunction for the rigid rotor. Let's have a look. So let's say, so finally, the normalized theta part of y is given. Let's write down what that is now, and we'll actually put in here the little m and the j. So again, we're going to recognize that this function is really based on these quantum numbers of m and j. And let's include now finally the normalization constant. So that's square root of that multiplied by pj with m as the superscript here, and that's that function of cosine theta. Let's remind ourselves actually what phi is, what capital phi is right now. So let's bring this all back in, and then we're going to combine them together. So that was equal to 1 over the square root of 2 pi. Okay, and multiplied by e to the plus e to the I m phi, and in this case m was equal to 0 plus or minus 1 plus or minus 2. So finally y is equal to, here's the final version, there's going to be something strange at the beginning in here. So we've got I to the m plus the magnitude of m, so I'm going to combine everything together. So we've got our 2j plus 1 over 2, and then of course we've got minus, so this piece is the same, or is it? Okay, what we're going to actually recognize is that there's the 2 pi in here from the phi function, so we're going to put that 2 pi is actually 2 pi to the half, so that conveniently fits inside the square brackets here. And then we have p j m, that's a function of cosine theta e to the I m phi. So that's our final y function. What's going on with this initial I term in here? It turns out that what happens here, we can actually think about this. So if let's have values of m in here, plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus 3. This ends up being a convention. And we basically recognize, of course, that I squared is equal to minus 1. I to the fourth is this minus 1 times minus 1 is equal to plus 1. And of course, I to the 0 is equal to plus 1. So we're basically going to find that when m is equal to plus 3, for example, we're going to end up with a, we've got the plus 3, so we've got I to the 6. which is -1 times -1 times -1. So this is going to give us a -1 value in front. It's just going to turn that function and make it be negative. When m is equal to +2 in here, so again, +2 plus 2 is I to the 4th. That was the one that we described earlier. So this is going to be a +1 term in here when n is equal to 1. So we're going to then end up with I squared. So this is going to be the -1 value in here. I to the 0 is +1. And then we're going to find that everything down, right, because we've got -1 in here plus the magnitude, so +1, that m term is going to cancel out. We're always going to have I to the 0. So these values are always going to be +1, +1, +1. So what we find is that, you know, if j is equal to 3, we go from when m is equal to -3, we have a +1 term in front of it. When m is equal to 0, we get a +1 term in front of it. When m is equal to +3, we get a -1 term in front of it. So these functions oscillate in sign, you know, depending on what the value of m is. So that's the final description here of the y function. It does have, by convention, this I term in front, which changes the sign of that function. What else can we do? So we can write our orthonormal set for the whole piece, for y in its entirety. And so let's start by writing this down. So we're going to have our integrals in here. So the theta function, okay, we get the d theta sine theta in here. We're going to have the phi piece in here. And by convention, and the convention that the textbook takes, we basically put the integrals to the left-hand side, and then we put the function in here. So remember, this is our function, and this m at the top is a superscript, not an exponent. And the theta and phi in here. Let's put the complex conjugate. Let's list that in here. Now we need this, right? Because in principle we have a complex number. Here's our complex number. Okay, the i's will cancel, but let's change that there for the complex conjugate, because wherever we see an I, we've got to put a plus or a minus I in there. So we might find that that's going to impact things a little bit. It will, in fact. Now we've got yj. We're going to call that j prime. And you know that the Kronecker delta is going to follow. So again, this is our shorthand notation, right? So this is equal to delta j prime. And also now we've got to recognize that, in fact, I've made a mistake. Instead of the m in here, let's use k, because we have to recognize that m and k are going to be different quantum numbers in terms of the phi portion. So this kind of takes everything into account now. This expression is our final shorthand that confirms or tells us, our shorthand that informs us of our orthonormality, the orthogonality, when either j is not equal to j prime, or when k is not equal to m, or it tells us the normality on the normalized piece where j is equal to j prime and m is equal to k. So you need both of those conditions to be true in order for us to get a normalized wave function. So let's state that. So y, j, m, theta, and phi in here are orthonormal with respect to sine theta d theta d phi. So not just d theta d phi. Okay, so that's why this sine theta term is in the left hand side. What else? I'm going to come to a conclusion in a second. In fact, let's see if we can fit that in down here. When r is a constant, and often we're going to call that constant 1, so we'll talk about this shortly, but when r is a constant, of course the volume element is, we know that already, is equal to r squared sine theta d theta d phi. You know, and let's say in fact when r equals 1, we get sine theta d theta d phi, and we're going to say that's equal to dA, and that is our surface area element. Just like we had a volume element, like an infinitesimally small volume element, this ends up being our surface area element for a sphere of radius r equals 1. So of course the surface area element would increase as r increases, but it's still constant, but that value is going to increase. So the point of this is I'm going to basically come to a summary and use that as a segue. So my summary, and this is kind of the final punchline, is basically because these harmonics, if you will, sit over the top of a surface. They sit over a surface for a sphere of a fixed value of r. There's a reason that we end up calling them spherical harmonics. So we're going to say these are orthonormal over a spherical surface, and we're told so called spherical harmonics. So the spherical harmonics are those eigenfunctions that are the solution to the Schrödinger equation for the rigid rotor. So we call those eigenfunctions the spherical harmonics. That's another word for them. So what else in summary in here? So the Schrödinger equation for the rigid rotor is, we found that to be h hat y j m. So it's spherical harmonics are in there as that y function equals, we'll look at that in a second. Okay, in fact this is the Schrödinger equation in its simplest form. So we've got the eigenvalue. The eigenvalue is this expression here, ringed in red. Let's actually write the longhand for the Hamiltonian operator, and that is equal to minus h bar squared over 2i 1 over sine theta di by di theta sine theta di by di theta plus 1 over sine squared theta. And you kind of have to go all the way back to find this several lectures ago. But also, when you do that, we also talked way back when we basically said that this was also equal to the square of the angular momentum operator over 2I. So what this means, right, is that actually if we look at the Hamiltonian operator, we've recognized as well that L hat squared is equal to minus h bar squared times 1 over sine theta, di by di theta, sine theta, di by di theta, plus 1 over sine squared theta, di squared over di phi squared. So it's more or less the same operator, right? So actually what this means is that these spherical harmonics that are eigenfunctions for the Hamiltonian operator are going to be eigenfunctions for the operator of angular momentum squared, right? So it turns out that because of this, so if we actually look at this expression up here, we can start to recognize that indeed this y function is also an eigenfunction. And so what's the key conclusion there in this sort of summary that we're going through here? I'll say, so these spherical harmonics are also eigenfunctions of L hat squared. So the key there, the Hamiltonian operator and L hat squared commute. What we can also say, if we look at our expression, if we think that the eigenvalue, remember, for the Hamiltonian operator is given on the right hand side of this expression in our Schrodinger equation, then we can also recognize that the eigenvalue for the L hat squared function is also going to be on the right hand side of this expression. So this is going to be our eigenvalue when the operator is L hat squared. So what we'll state in here is that L squared is equal to h bar squared j times j plus 1, and j can take on values 0, 1, 2, etc., as we know. Okay, so this is a very special relationship between energy and the Hamiltonian operator and angular momentum squared, and we're going to find that that's quite important as we move forward into the next section. So thanks for listening. We've solved the theta equation. We've already solved the phi equation after sort of using our separation of variables approach to breaking down y. And so we find that y is the spherical harmonics, that these are the eigenfunctions. These eigenfunctions are essentially eigenfunctions for the operator equation involving the Hamiltonian operator and the operator equation involving the angular momentum operator squared. So thanks for listening, and we'll see you next time.